Yes?
Hello. About the exercises, are we going to correct them?
Yes. So if you tell me that you did it, we do it next week. Say Monday. Okay?
Yeah, we finished it, I think.
Very good. So let's do it Monday. Is it okay?
Should we have a scan file to you for you to check it out, or?
So tell me, let's see. Can we discuss at the end of the lecture to find the best? Because I think the greatest would be just to discuss collectively. Okay? So either I just show you the result, or some of you can you, so if you share the screen, do you have a way to write on some, so that
I think, for example, you can send us the solution to the one day before the correction, and then if we have questions, we just post the questions always, instead we don't need to go through all the stuff.
No. I want to hear you. So it's, I prefer, this is a good chance so that you present your argument. Okay, because if I would prefer, because it's a way to discuss and, okay? I can send you the solution, but I think it's much nicer if we just share all together, okay? So, let's say, let's do it Monday. Today I'm going to discuss perturbation theory. As I told you Tuesday, perturbation theory is a way to study approximate solution of the Schrodinger equation. Okay? So, and for the time being, today and probably Monday, we will discuss the first case, which is time independent. So, what does it mean time independent perturbation theory? The problem is the following. Suppose that your system is governed, you have a quantum system which is governed by an Hamiltonian, which can be written as in this form. Okay? So it's H 0 plus lambda v. Now, suppose for example, so assume that you are able to solve the problem for H0. So, you know everything about H0. You know that H0 has eigenstates that I call phi 0 n with associated energy E0 n. Okay? So, this is something you know. You know both phi 0 and you know E0. Then the question is, how do I determine the eigenstate and eigenenergy of the full problem? Okay? This is something we want to determine. Now, when lambda is 0, then you know the solution, because the solution is nothing else than the one that by construction you know. So the solution is phi n will be phi 0 n and En will be E0 n. Now, you may assume that when lambda is sufficiently small, then the Hamiltonian H will be very close to the Hamiltonian H0. And so, since it's close, you may expect that also the eigenstates and eigenvalues will not differ much. Now, what does it mean small? What does it mean it does not differ much? All these things should be well defined. I mean, now I'm just blind, but I'm just giving you an idea about the strategy. And the strategy will be that by using phi 0n and E0n, I will have a way to construct phi n and En in a kind of iterative way. Okay? This is perturbation theory. Now, the smaller is the correction that I'm imposing to the Hamiltonian. So the smaller is this term. The smaller number of terms I will need in perturbation theory. So essentially what I'm going to do is that I'm going to simply express this phi n as a Taylor expansion in powers of lambda. So I will have a term which is lambda 0, lambda to the power 0, then lambda squared, lambda cubed, and so on and so forth. And each term can be determined only by knowledge of phi 0, n, and E0, n. Now, when do you have to stop in perturbation theory? Should you stop to the first order, second order, third order? Well, this depends on the problem, on the value of the perturbation and the nature of perturbation. But of course, perturbation theory in general will be efficient if you need only few terms. Okay? So perturbation theory is something which is useful when the starting point that you know very well, so meaning H0, is something that is already quite close, in a sense, to the solution of the system you want to consider. So before I am going to discuss the general structure of time-dependent, independent perturbation theory, I will study with you a very simple problem, which is, however, very important to understand a few things.
Professor?
Yes.
Okay, I just want to ask, what do you mean when you say Hamiltonian zero, like H naught?
So, the only meaning to that is that the Hamiltonian H is the Hamiltonian that you want to study, and in many cases you are able to split it in a part that you know how to compute, so for which you know all the spectrum, and the rest, and something else which is very difficult. Let me make an example, okay? So just take, for instance, one single particle, and then you have p squared over 2m plus v of r, okay? So you have single particle, this is the kinetic energy, and this is the potential, right? Now, do you know how to solve this problem? Not really. I mean, for a generic V, I mean, there are cases in which you know how to solve the problem, there are cases in which you are not able to solve, right? But, for instance, suppose that V is very small for some reasons. So this is I call it H0, and this is what I call V, okay? Then you see H0 is a reference Hamiltonian for which you know all the eigenstate and eigenvalues, okay? These are plane waves, and the eigenvalues are h bar square, k square over 2m. So you use this to construct the solution of the full problem, the approximate solution of the full problem. Is that clear?
Okay.
I don't know, is it clear, yes or no?
Yeah, it's clear.
Okay, good. So let me give you another example, okay? So you study the harmonic oscillator, okay? So the harmonic oscillator, one dimension, you have p squared over 2m plus 1/2 kx squared. Do you know how to solve this?
Yes.
Okay. Now suppose that you put here lambda x to the power 6. I mean, this problem is something you don't know how to solve in general, okay? But then you say, okay, I know this, and I call this H0, and this is just lambda b. Now, if this is very small, then I have to specify, and I have to tell you what does it mean very small, then I can apply perturbation theory. Okay? So, I think then it is very important that you understand what can you call H0, what is V, and I mean this is something which depends from case to case. Because you see, if you look at this problem, then there is not a unique way to choose H0, because you can say, okay, I choose this as H0 and then I treat this as perturbation. This is a possibility, but then if K, so it becomes strong, then this is not a good choice. And then you say, okay, I just take this as H0, and then this is a perturbation. And so you may find different regimes depending on the choice that you are making on the reference Hamiltonian H0. Okay? As I said, I want to consider a simple problem, okay? That I can study exactly, and this will teach us a lot of things. So suppose the following. Suppose that you have a two-level system, okay? So a system which is characterized by phi 0, 1 and phi 0, 2, okay? And so these are the two eigenstates of H0. This will have an energy E0, 1, and this will have an energy E02. Okay? So H0, if I write as a matrix, using this as the basis, I will have H E01, E02, 0, 0. Is diagonal. Okay? Now, I want to actually study the following problem, which is h0 plus lambda v. And I want to study the eigenvalues and eigenstates of this new problem. So let me write H using this matrix representation because it's much simpler. So H will have the form E0 1 plus lambda V11. Then I have lambda V12, lambda V21, E02 plus lambda V22, where Vij is just phi 0 I V phi 0 J. Okay?
Yes.
Very good. So this is a very simple problem. So I want to just find the eigenvalues. Okay? Now, the eigenvalues are simple. I mean, it's just a quadratic thing. So I give you the result just because I want to describe. You get that the new eigenvalues are equal to E01 plus E02 plus lambda V11 plus V22. Okay? Plus minus. Okay? I just write here not to. And then you get the square root of E01 plus lambda, E02 lambda V22 minus E01 plus lambda V11 divided by 2 squared plus lambda squared V12 squared. Okay? This is the result. Now, let's consider. Look, this is, this is just finding the roots of a quadratic equation, so it's nothing. But I would like to discuss this result. So once you have the eigenvalues, of course, you can find the eigenstate. Now, let's consider this expression, and let's discuss it in some more detail. So there are two cases which are very important to be considered. And the two cases are related to the fact that the two unperturbed eigenvalues are non-degenerate or degenerate. Okay? So I may have two situations. The first situation in which the spectrum I'm considering has some degeneracy, so E01 is equal to E02, or the case in which the spectrum, in this case it's just two levels, is non-degenerate. So I have E01 different from E02. So I will consider first this case. So I will consider the case of non-degenerate spectrum. Okay? If I consider the case of non-degenerate spectrum, then I can just proceed and expand this in power of lambda, okay? Just doing Taylor expansion, and I will find the following result. So I will have that E plus will just be equal to E20 plus lambda V22 plus lambda square V12 square over E02 minus E01 plus other terms. Okay, I'm just stopping to second order in lambda. The other term is just E minus equal E01 plus lambda 1 minus lambda square V12 squared E02 minus E01 plus other contribution. So let's observe the result. So just take one of the two. Okay? So let's take this one. So the lowest eigenvalue. Now the first correction is just lambda times V11. But V11, I remind you, is nothing else that phi 01 V 501. Okay? So the meaning of V11 is nothing else that the average value of the perturbation computed on the unperturbed state 501. So the level, the energy level will just shifted just because this extra perturbation will have a contribution to the energy, which is just the average of the unperturbed state. Then the next is much more complex. Okay? Is already more complex because you see the terms related to lambda square just connect, just mixes the two levels. You see here there is a term which is V12. Okay? I mean, it's not that it's just a rigid shift of the related to the unperturbed state phi01, but also matrix element of the two different levels enters into the game. And this is related to the fact that the phi zeros 1 and phi 02 are no longer eigenstates, and so the new eigenstates will be a mixture or just superposition of these two unperturbed states. Now, by looking at this expression, you can learn something important. So you can just make sense of what I mean by saying something is small. The perturbation is small. Because you see, so essentially for perturbation theory to be valid, the various terms that I'm putting here, they should introduce some very small correction, okay, to the bare result. So you see that in this particular case, you see that what is important is that lambda times the transition element V12 should be much smaller than the gap between the two eigenvalues. So what is really important is not that lambda should be smaller than 1 or something, because this does not mean much. But we have to compare the spectrum, and so the energy difference between different eigenvalues of the unperturbed states with the matrix element that connect them. Okay? So, in this particular, you will see that if this is small, then this will propagate, and also other terms are small. Now, what happened? So this, in a picture, means the following. So if you plot here E1 and E2, okay, and this is lambda. So this point lambda is 0 is just E01 and E02. Then when you just put lambda, then you will have something like this. Okay? I'm just inventing. But there is just a slight modification. So it's not that you are mixing up too much the spectrum. So something like this, just a crossing, this is not something that can appear in perturbation theory. Okay? You will just see some slight modification to the unperturbed spectrum. Now, a case in which this slight modification is never there is the following. Is the case in which you consider a degeneracy. And the degeneracy here means, the general spectrum means that you are taking E01 equal E02. So let's analyze this in some details. Okay? If you take E01 equal to E02, so this will simplify, and so what you get is E plus minus is equal to lambda V11 plus V22 square divided by 2 plus minus lambda V11 minus V22 minus V11, okay, square divided by 4 plus, okay, do you see that?
Plus or minus?
Where? Yeah?
V22 minus V11 or V22 plus V1
This is
inside the
here? Minus. I'll just write it again. Okay?
Professor. I think there is a E1 plus E2 over.
Yes, sorry, I forgot to say. E1 plus E2, since this is a constant, it's just a shift. I will forget, okay? But you're right. I want to write it. I forgot to say. It's just E0, because E01 is equal to E02, okay? So I just call it E0. Huh? And consider the degenerate case. So this will be present in both.
We also do that inside the square root, right?
No, because inside the square root they cancel. It's E0. Here there was E02 minus E01.
I see.
So they cancel. So it's just a shift. You can forget about it. Okay? So if you want, I can write it better here. So you have E plus minus is equal to E0 plus lambda . Okay?
Yes. Professor,
Yeah.
I have a question. So does this mean that the non-degeneracy in the original Hamiltonian H0 will lead to the non-degeneracy in the
Yes.
Hamiltonian with the perturbation, and also the degeneracy in the H0 will lead the degeneracy to the H?
This is a very good question. I will tell you in a second. Now, in this particular case, the degeneracy in the H0 is lifted, is eliminated by the presence of the perturbation. Okay? So you had two states which were degenerate in H0, but then when you put the perturbation, they are non-degenerate. For instance, if you take a spin 1/2, okay? A spin 1/2, just take as a basis up and down, okay? So if you put a magnetic field and you consider just a perturbation, I mean, this is much more complicated. But then the two states are split, because now up or down they will have different energies. So in principle, when you add a term in the Hamiltonian, depending on the nature of this term, the sum or all the degeneracies present in the spectrum may disappear. Okay? Now,
Okay, so what I want to ask is there a case where perturbation will make a new degeneracy appear or not?
no. So what can happen is that if you have a degenerate spectrum, then perturbation may or may not lift the degeneracy. Okay? Now, what can happen is that if you have an Hamiltonian and you add an extra piece, then you may have a degenerate spectrum. This can happen, but this will not happen in perturbation theory, I would say. But in principle, yes, it may happen. Degeneracy is always related to some symmetry in the Hamiltonian. Okay? So you may have a situation in which you have a non-degenerate spectrum and you just add a piece of the Hamiltonian which restore some symmetry, and then you will have appearing degeneracy. But this will not happen in perturbation theory. Okay? Because you have to, this particular case that you are mentioning will appear only if you are adding terms which are of the same order of the unperturbed Hamiltonian. Okay?
Also, by this you're saying that perturbation actually breaks the symmetry of the Hamiltonian.
In this case, yes. So in this case, for example, just break the symmetry. No, but let me go step by step, okay? So what I'm saying is that by adding V here, breaks the symmetry, because you had the degenerate spectrum and then something else happens, okay? But something which I want to point out is that you see that the correction to the spectrum here will depend on the lambda, absolute value of lambda. Okay? Which is not something you can get in Taylor expansion. Okay? And the reason, if you wish, is related to the fact that here is not that you are, I mean, basically you are starting a situation in which you have two degenerate level, you apply something which can be arbitrarily small and the spectrum is splitted. So it's not something that is happening in a continuous fashion. Okay? If you go to a double degenerate to a single degenerate at any value of perturbation, this is something which is not a continuous thing. This means that in the case in which we have degenerate eigenspectrum of the unperturbed Hamiltonian, then we have to be careful and do perturbation theory in a slightly different way. Okay? So when you have non-degenerate spectrum, the first case that I wrote, then you have this case in which you compare the matrix element to the gap, and then say matrix element times lambda to the gap, and then you could say, look, matrix element times lambda should be much smaller than the gap, and this gave you intuition and understanding on when the perturbation is small as compared to H0. If you start in the case of two degenerate levels, the gap is 0. So you don't have this concept of smallness of perturbation compared to the Hamiltonian. Okay? So you have to introduce some extra care, and we will see that doing perturbation theory for non-degenerate levels will be slightly different than doing it with degenerate levels. Okay? So the first thing we are going to do is just to study perturbation theory in the non-degenerate spectrum. So what I'm going to do now is just give you the general formulas, okay, or the general approach, and then we will start studying some specific cases. So we want to do non-degenerate perturbation theory. So you have H0, you have H, which is equal to H0 plus lambda V, and H0 is such that H0 phi 0 of n is equal to P0 of n phi 0 of n. Okay? And basically you just say it's non-degenerate spectrum. Okay, so essentially E0 n is different from E0 m if n is different from m. Okay? So, perturbation theory is constructed in this way. So we have to solve this problem, okay? H0 plus lambda v phi n is equal to E n phi n. So we have to solve this problem. Now, I point out, and this is very important, since I'm considering a non-degenerate spectrum, then the eigenvalues and the eigenstates are identified by the quantum number n for any value of lambda. So basically there is a one-to-one correspondence of the eigenstate and eigenvalue of lambda equals 0 to the corresponding one when lambda is different from 0. So what I do is then I just say, okay, I just construct phi n in the following way. Just say that this is phi 0 n plus lambda plus lambda square okay? So I just write down in power of lambda the eigenstate, and the same way En is equal to E0n. Yes.
They are all phi n times lambda.
I do not hear. Can you repeat?
Phi n, the expression of phi n.
Yes.
Phi n is 0 plus lambda times phi n is 0, right?
No, I'm just saying you just write phi n, the exact eigenstate, as a power expansion of various terms. So the term which is the one when lambda is equal to 0 will be phi 0n, which is this solution here. Okay? When lambda is different from 0, you just say, okay, there is some extra contribution, so it's lambda, you see it? Lambda phi 1, I call it phi 1. We don't know what is phi 1. This is something we have to determine. Okay?
Yeah.
So this is just the first correction to the eigenstate n. This will be the second correction to the phi state n, so on and so forth. Okay? Now, the same is true for the eigenvalues. So we'll have E1n, lambda plus lambda square E2n. Okay? We don't know what is so we don't know phi 1, phi 2, phi 3 and so on and forth. We don't know E1, E2 and so on and so forth. The task is to determine them. Okay? So how do we determine them? So remember that it's non-degenerate spectrum. So what I do is to just take this, yeah.
The reason for which we explain the phi n and En is because the lambda is small.
Yes. So it's very important. It's the perturbation small. You see, if I tell you, so if I ask you when the lambda is small, so is lambda small, which is when it's 10 to the minus 2 or 10 to the minus 3 or 24, you don't know. So you have to compare objects which have the same physical dimensions, okay? But this is what you say is true. I'm just trying to construct this in a series expansion because I can stop at some point, okay? And now I do what you said, so I just take this expansion and this expansion and I plug into the Schrodinger, so in the eigenvalue expression. So I just try to write it as 0 plus lambda v, and then I have phi 0 n plus lambda phi 1 n plus equal, and then I have E0 n plus lambda E1 n plus and I have the phi, okay? So in order to satisfy this equation, then basically I have just to equate terms which are the same power of lambda, okay? So let's see the zero order term. The zero order term is this times phi 0, E0 phi 0 of n should be equal to E0 of n phi 0 of n, okay? And this is satisfied because by construction phi 0 is, we chose to be the eigenstate of H0, okay? Can I remove it? So let's,
No. I wanted it.
sorry?
I still wanted what you removed.
Okay, so but just check your formulas and just equate the zero order term. Then you will see that it's just the eigenvalue equation for H0. Do you see it? Hello?
I mean, I different.
So the zero order term is this times this, which is H0 phi 0 n equal, and here this is the only term, which is E0 n. Okay? So this is the Schrodinger equation, so the eigenvalue equation for the unperturbed case, which is satisfied because we chose phi 0 and E0 using this condition. Okay?
Yeah, okay.
So tell me, now we just look at the first order term. Okay? So from this side I will have V times phi 0 of n, okay, plus this times H0, H0 phi 1 of n is equal to E0 of n phi 1 of n plus okay. Is it okay or not? This is first order in lambda.
Now can you repeat the second part?
This one?
Yes.
So the first order in lambda is when I multiply 0 order times lambda phi 1, and here I have either E1 and multiplied by phi 0 n. Okay?
Yes.
Yes.
Is it clear for everybody?
Yes.
Yes.
Now, I want to write it in a more compact way, so I just bring this on this side and this on the other side, okay? So I just get H0 minus E0 of n phi 1 is equal, sorry, I just write plus V minus E1 phi 0 of n is equal to 0.
So, I think En0 is multiplied by En1, so we can write H0 minus En0.
Just a moment. So, okay, can you repeat again, because I'm not...
I said
Where?
En0 is multiplied by En1, not En0. You cannot, yeah, put this.
But this is Vn1.
Is it one?
This is 1.
Okay.
Okay? So this is Vn1. Okay?
Can you rewrite the others also? 0
Yes. Okay. So I just take this is phi 0, this is phi 0, this is phi 1, and this is phi 1. Okay? So I just write as this term H0 minus E0 and phi 1, okay, of n plus V minus E1 n equal to phi 0 n, okay?
Yes.
Now, I want to determine so I just write here that phi n is equal to phi 0 of n plus phi lambda phi 1 of n plus, and the same is true for En to E0. Now, multiply this equation by phi 0 of n. What is the result? This term becomes what?
Sorry, Professor.
Yeah.
I cannot see the right-hand part of the work now. That's on top of the chalkboard. Right hand.
This one?
Yeah, they are not clear to me.
Okay, I'm just rewriting the expansion of phi n and en. You have it written. Okay? I rewrite it, okay? So, let's say I write it here. This is phi n. I want to that you remember that this is phi n and this is En, okay? Hello?
Yeah, it's okay.
Okay. So, I take the first order correction, which is this equation, and I just multiply with a bra phi 0 n. Can you tell me what is the result? So what is, when I multiply this here, what do I get?
Minus EN1 in
So just step by step, because otherwise I don't understand. If I multiply the first term, which is phi 0 of n, h0 minus
0.
0.
Okay, very good.
Yes.
So this is 0, and what I get here, I just get
minus 1.
phi 0 of n v phi 0 of n minus e1 n equal 0. Okay?
Yes.
Very good. So this means that E1 is determined, because this is something you know how to compute, because V is known and phi 0 of n is known.
Yes.
So this is exactly the same as that you found in the two-level example, in which the first correction was V11. Huh? So,
Yes.
okay, can I erase it? Say yes?
Yes.
Okay, so E1 is done. Then, what you need to know is to determine, so this is something we don't know. One we know. We don't know phi 1 of n. Okay? This is something we don't know. So, what we multiply is by phi 0 of m with m different from n. Okay? What do we get? So here I will get E0 of m minus E0 of n phi 0 of m phi 1 of n. Right? From this term here.
Yes.
From this term here, I get plus phi 0 of m v phi 0 of n, and this last term is what? Is 0. Okay?
Can you repeat the first one?
So I just
We multiply both sides by the sign and 0.
yeah, with m different from n. Okay? So when I multiply phi 0 on this term, this will become E0 m minus E0 n. Okay?
Yes.
Times phi 0 n phi 1 n. Okay? So I remind you that m here is different from n. Then I have to look at this term. Then when I multiply phi 0 of mv, I get this term here. The matrix element between m and n of v. And then I have the last term, which is 0, because I will get something like minus E1 of n phi 0 of m phi 0 of n. But this is 0 because I said I'm taking m different from n. Okay? Okay?
Yes.
So this is equal 0. Good. So look here. What is really not known is this one. This object that I will tell you in a second. So I just find this object that is I get phi 0 of m phi 1 of n equal phi 0 of m v phi 0 of n, and then I get divided by E0 of n minus E0 of m. Okay?
Yes.
Now, can I erase this so that I write here? Can I erase it?
Yes.
Okay. So I just rewrite this up here because it's useful for me. So I found phi 0 of m phi 1 of n is equal to phi 0 of m v phi 0 of n divided by E 0 of n minus E 0 of n. Now, what is this? This is nothing else that the component of phi 1 on the state m. Because I can always write phi 1 of n as sum over m over c m phi 0 m. Okay? So I can just write the state phi 1 as a superposition of phi 0. I just use this as a basis. But if I do like this, then this Cm are nothing else that phi 0 of m phi 1 of n. Okay? That's the definition. Okay?
Yes.
So, you see that in this way, at the first order, we found the correction to the first eigenvalue. So we found that E1 of n is just phi 0 of n v phi 0 of n, and we found the first correction to the eigenstates. Okay? Now you see, now you have that information, so you know what is E0 E1, phi 0 and phi 1. Then you can proceed and take the second order, the term proportional to lambda square in this equation, and you just write a similar equation for the lambda square term. You do it, so this is something you have to try to do it, and then what you will determine are phi 2n and E2n.
Can you repeat what we should do?
Yeah. So we did. So now you have to determine the second order correction.
You mean phi2?
Yeah.
Okay.
And E2. Okay? And you will see that since you know phi 1 and E1, phi 0 and E0, then this is something you can do. Okay?
Yes.
Now,
So, quick question, just PA1 is equal to PA1 PA0, right?
this one you're asking?
Yes.
No, this is phi 0 n v phi 0 n.
Okay, yes.
Okay? Now, there is one important thing that we have to discuss. Now, when I write phi 1 n, then you see that I did not say anything, but if you see, if n is equal to n, this expression blows up. Because this denominator would...
Yes.
And in fact, this was determined under the condition n different from n. Okay? Now, you may ask yourself, okay, why there is no component to the first order of phi 1 which is along phi 0 n? Okay? So what I'm claiming is the following, that m here is different from n. And you say, why shouldn't I consider also n equal n? Okay? Let's see. Can I erase here?
Is that because we expand the original phi, and like we take phi n 0 and phi n 1 as basis, so they must be different.
Why? I did not understand why. Can you repeat?
I mean, because initially we expand the wave function into sin 0 and sin 1.
No,
and sin
no.
2.
No, this is not the reason. Let me discuss. Just a moment, okay? So do you see better when I write here or here? Here?
Yes.
Okay. Okay, so I just write here. So I just write phi n. We said it's equal to phi 0 of n plus lambda phi 1 of n plus lambda square phi 2 of n, so on and so forth. Okay? This is what I wrote so far. at the beginning. Now, by construction, phi 0 of n, phi 0 of n is normalized, is equal to 1, okay? However, also phi n should be normalized, okay? So the state that we are determining, phi n, the eigenstate of H should be normalized as well, right? Now,
Yes.
let's discuss about normalization, and then I go to the... So, suppose that I stop at a given order in perturbation theory, okay? Suppose that I stop at the second order. Let me close the window, otherwise it's noisy. So, I want to stop a second order in perturbation theory. Okay? Now, can I get exactly 1? No. Because if I stop, so I'm computing the state in an approximate form. Okay? So, I have to do phi 0 n plus lambda phi 1 n plus and the same is phi 0 n plus, okay? So I have to do all the cross product, and I would find 1 plus something, okay? In general, I will not find always 1. Now, am I doing something correct, or am I doing something wrong? Well, when I do perturbation theory at a given order, then it means that I'm going to make mistakes which are of the order lambda n plus 1, okay? So if I compute the eigenstate and eigenenergy to the order lambda square, so I'm missing correction which are of the order of lambda cube. Is it clear?
Can you repeat, please?
Yeah, so if you do a calculation in perturbation theory in which you are doing, you are stopping at second order in lambda. So this means that you are doing a calculation which is accurate to order lambda square. So in principle you are making mistakes which are proportional to lambda cube, at least. Okay?
I thought it should be proportional. I mean, when we increase the order, so we will move to more correct answer.
Yeah, well, what does it mean more correct? That your error will be lambda cube or lambda fourth, lambda fifth, okay?
It means like we move closer to
No, right,
to the,
but I want to know what, just quantify, what does it mean closer? So it means that if you are doing a calculation which is up to 10th order in perturbation theory, the mistake you are making will scale like lambda to the power 11. Okay?
yes.
So what you say is correct, but then I want to quantify. So, and this is, okay, so this means that when I compute normalization, then if, for instance, I stop at the second order, so I should get 1 up to terms which are of the order of lambda cube. So so normalization of the state should be guaranteed up to the order that you are evaluating. Is this clear?
Yes, yes.
Yes.
Okay? So when you do a perturbation expansion and you find the eigenstates up to first order, second order, third order, whatever, you should not try to normalize to 1 exactly, because this is useless, because the calculation is only valid up to a given order, and also normalization should be guaranteed up to that order. So this is an important piece of information. Now, I want to consider, I want to go back to the question that I asked before. So the first order in phi 1 n will not contain the component n. Okay? And I will show you why. So suppose that you have phi of n, we said is equal to phi 0 of n plus phi lambda phi 1 of n. And we said that phi 1 of n we can write, for the moment don't care about the exact expression, but we can write as phi 0 of n plus lambda sum over n of Cm phi 0 of m. Okay? I just write phi 1 in this basis. Okay? And then there are terms. Okay. Now, here I really would like to identify the m equal n term and the rest. So just write this as 1 plus Cn lambda Cn phi 0 n plus lambda sum of m different from n of Cm phi 1 n m. Okay? If you don't see here, I did nothing terrible. I just take the term in this m, in this sum, the term which is n equal n, and I just collect it here, and this is the rest which is m different from n.
Yes.
Okay?
Yes.
But I was still thinking that the summation will be with psi at 0.
You're right, sorry. Yes, here. Yes, you're right. Very good. Okay? So now I want to compute, so this we said is phi 1. So this is phi n, sorry. Okay? So then I want to compute phi n to the first order, I mean just in this case. So then I have 1 plus lambda c star n phi 0 n plus sum over n different from n of c star m phi 0 of m times
the sum is times lambda.
sorry?
I mean lambda times the sum. Lambda.
Here, yes. Times 1 plus lambda Cn phi 0 of n plus lambda sum over m different from n Cm phi 0 of m. Okay? So let's see. I am this times this, and I get 1 plus lambda Cn modulus squared. Okay? So this times this. Then I the terms of first order in lambda, they are 0, because you see I have to, for instance, multiply all the terms in the sum with phi 0 of n, but since m is different from n, the scalar product is 0. Okay? And then there is a term which is lambda squared. So when I multiply this, so then I have lambda squared sum over m Cm modulus squared. Okay? Now, as I said, since we are doing a calculation which is valid for the first order in lambda, then corrections which come from lambda square we can forget. They are beyond our approximation, and so we can simply forget. It's not the problem. But you see, the problem arises here. So if I explicitate this, I get 1 plus lambda, so 1 plus lambda Cn plus C star n plus lambda square.
Sorry, Professor, could you just repeat why we neglect the higher order terms?
Yes, because I'm doing, see, if you do a calculation which is valid up to first order in lambda, then we can forget about corrections which are higher than the first order.
Okay.
Look, I'm saying something very stupid, but just to let you know what I mean. So suppose that you do a measurement in which you know that the error is on the second decimal digit, okay?
Yes.
Now, if during the calculation your computer will give you 64 digits, you can forget about those, okay? Because you know that only the first two digits are important, okay?
Yes.
It's the same logic here. If you are doing a calculation which is valid to the first order in lambda, then correction to the lambda square should be ignored, because you are just not including all the terms consistently, okay? So they are just like non-significant, so you just put it 0. So that's why you forget about this. Okay? So you see that here I just get this term here. Now, you see that this is lambda square, and again with the same logic I ignore it. But then you see that here I have a problem, because I get the correction to the normalization which is linear in lambda. So this tells you that if you do a calculation to the first order and the wave function should be normalized, the only option you have is that the coefficient of the state, which is belonging to the n component, should be 0. So this Cn should be 0. So coming back to what we wrote at the beginning when we wrote phi 1 as sum over m of Cm phi 0 of m, this is phi n, then you will find that Cn in this expansion should be 0. And in fact, what you found is just the component phi m, phi 1 of n, when m is different from 0. So this, so there is no correction along the state n. All the correction to the second order are proportional to phi, to the, they are along the components m different from n. Okay? Good. So that's it. So try to do the following. Try to determine the second order correction to the states and the...
Sorry.
Yeah?
I was a bit lost. In the how did you get the modulus of 1 plus lambda Cm squared? And
because I split the sum here as I just took out the term m equal n and I put it here. Okay? So the only thing I need is that to multiply this term with this term and I get this.
and why is it equal to the next term?
No, it's not equal. I'm saying that there was here also a term which was lambda squared, Cn modulus squared, okay? And other terms. I said that all these terms in proportion to lambda squared we ignore, and we have to worry only about the linear term, which is the one we have to consider because the calculation is valid to linear order in lambda. But then you see that if the coefficient n is different from 0, then normalization can never be obeyed. And the only way in which normalization is satisfied is that Cn is equal to 0. Remember that phi 0 of n is normalized.
Oh, okay. Actually, it's still not clear somehow to me. I'm very sorry.
Don't worry. So I propose the following. You just do the calculation. So the only thing, I tell you what you have to do. You just look for the normalization, okay? So you have to, okay, and then you have to remember that phi 0 n is also normalized. Now, you have to verify that there is no way in which both the 0 order and the state to the first order are normalized if Cn, the component n, is equal to 0, is different from 0. I would suggest the following. You just try to do the normalization. If you don't manage, you just write me and then we discuss, I don't know, today or tomorrow.
Okay, I'll try.
Okay? So I thought, yeah? So next lecture is Monday, okay? So I wanted to tell you something else. Now, if you want to, so we cannot meet in person, but if you want to discuss about exercise or some other thing, then we can fix an appointment in the terrace. Let's say it should be 1 or 2 at most. We stay very distant, but then we can discuss on the blackboard, okay?
Yes.
We can in the terrace where we have also the cafeteria and open space. But if you are 1 or 2, we can discuss about either the lectures or. So you are in total 8, right?
Yeah.
So
Yes, but there is one who has to watch the video.
Okay.
What do you do?
Okay, no, what I want to say is that we can meet, if we just have groups of 2 people, at the time we can meet to discuss specific thing besides the lectures. That's what I want to say. Okay? Okay, bye-bye. Let's go for lunch. Ciao.
Bye.